Oh, I see. Yes, I think I remember that. Well, I hope you like the comments.
There's no rush.
I have a military training.
Yeah, I won't be long. But yes.
Okay, we're going to get resume the last talk from the morning session. Our speaker is Sberna from Nottingham. We'll read more about that.
Yes. Thank you, Luis, and thank you to the organizers for inviting me. I'm going to continue along similar lines from where Zheng left off, talking about linear black hole perturbations. And in particular, I want to explore more the question of how black hole quasi-normal modes get dynamically excited. And I want to put this in the context of gravitational wave astronomy. Typically, we say that quasi-normal modes describe the ring down, so the final stage of a binary black hole merger at intermediate times. In gravitational wave astronomy, this means that at those times, the waveform is described by a superposition of these damped sinusoids, these complex exponentials with some amplitudes and phases. And these amplitudes currently in waveform models and in data analysis are taken to be constants. And they're obtained in various ways by fitting numerical relativity simulations. They can also be left unspecified and determined directly from observations. Or they can be modeled in some cases, assuming that the secondary black hole is very small, is just a point source plunging into the primary black hole. There are, of course, clear limitations to this because in the full waveform, we want to connect the ring down to the previous stages of binary evolution. And these quasi-normal modes need to be excited at some time to turn on in some way. So again, in current waveform models, there are some ad hoc turn-on functions, activation functions, to be able to connect these stages. But of course, we would like to do better. As Zheng mentioned, we think there are nonlinearities excited in the ring down, and we can imagine that they would be most excited exactly in that same region when linear quasi-normal modes are also excited. Also, higher quasi-normal modes with higher overtone number decay rapidly, right? So they are most observable right at the beginning of the ring down. So, and of course, the signal is also largest in that region, right? So there's many reasons why we want to understand the dynamical excitation better. So in this talk, I'm going to take two different approaches. First, I'm going to look at quasi-normal modes as mode solutions, so in frequency space, but I'm going to try to move towards the dynamical picture by using different coordinates rather than the standard Boyer-Lindquist coordinates, and using hyperboloids. And in the second part of the talk, instead, I will abandon partly this mode picture and use some time domain methods. So let's start with the first part. This was work with Marika Minucci, a postdoc at, I think, the Niels Bohr Institute right now, with Panosso Macedo and Cristiana Pantelido. So to understand one important feature of quasi-normal modes, which you've heard about in Steven's talk yesterday, is that they are orthogonal under a suitable bilinear form. And this is to remind you what the bilinear form looks like. It's composed of a conserved current, the symplectic current of the Tchaikovsky equation, and the insertion of a symmetry operator of Kerr, the T-phi reflection, which is playing a double role here. It's ensuring orthogonality, and it's also mapping S to minus S solutions. But one challenge with the bilinear form was when we were using the standard Boyer-Lindquist coordinates, was that our quasi-normal modes were actually divergent at the two boundaries of these slices, at the bifurcation surface and at spatial infinity. And in Steven's talk, you heard that many people have proposed ways of regularizing quasi-normal modes in these products. For example, you can use a complex contour which goes around this branch cut of the mode functions that originates at the horizon. So going around this problem is one reason, on top of trying to move towards dynamics, to try and use different coordinates. So here come, therefore, the hyperboloidal foliations, which are essentially, these slices that connect to the more interesting boundaries of our space-time, the future horizon and future null infinity in this case. They are built quite simply with a coordinate transformation that mixes the time and spatial original coordinates. And to simplify the quasi-normal mode problem further, you can also do a spatial compactification and a conformal rescaling to absorb some of the spatial scaling of the mode functions. These are the future hyperboloids, but you can also build past hyperboloids that connect the past horizon and past null infinity. And the difference is just a sign over there. And here I'm going to use as the height function, this function that is, producing your hyperboloids, this form here, the minimal gauge, known as the minimal gauge. So the power of these hyperboloids is that not only they connect to these nice regions of the space-time, but they also regularize the QNM solutions. So in particular, QNM solutions that are regular on future hyperboloids are the retarded QNM solutions. So they are outgoing at those future boundaries, while QNM solutions that are regular on the past hyperboloids are instead outgoing at these other boundaries down here. Okay, so that's very nice. And so based on this, you could have hoped that the bilinear form would now be regular on the hyperboloids. Unfortunately, this is not the case. And this is because that T-phi reflection that we have to insert in the bilinear form in order to obtain orthogonality is actually mixing retarded and advanced solutions. So it's mapping one into the other, or mapping future hyperboloids and past hyperboloids. So that means that if I want to look at the orthogonality between two retarded quasi-normal modes, one of them is going to be mapped into the advanced solution and is going to be irregular on the hyperboloid that I've chosen. By the way, I know that I'm the third talk of this morning, so I've sprinkled some cats throughout my slides. If you get bored, you can count them. Okay, so because the bilinear form is still, divergent, not well defined on hyperboloids, we realized that we still needed to resort to regularization. But this was quite simple because we could just, do a coordinate transform to the contour we were using in the coordinate R to this new contour in the hyperboloidal coordinate sigma. And, it takes a funny shape, but it performs the same task. And so once you define the bilinear form on that contour, you can find that it's finite and independent of the slice you take. Okay. But going back to the dynamics, so far, the way to establish how quasi-normal modes are excited is to compute their excitation coefficients. And in Stephen's talk, you saw how these were connected to the bilinear form. And we find exactly the same in the case of hyperboloidal slices. So if you have some initial data on your first hyperboloid, you can project it and normalize it using the bilinear form to find these excitation coefficients for the quasi-normal modes at late times. And you can check this explicitly comparing term by term the expression on the right with what you would obtain with the Green's function. However, the excitation coefficients themselves cannot be the whole story when we talk about the dynamics of quasi-normal modes. Because again, these are just constants. And for example, they're not accounting for any causality, for the fact that it will take some time for all the initial data to come into causal contact with our observer. They also don't take into account the fact that we might have time-dependent sources like the particle that will eventually generate the ring down on the right-hand side of the Tchaikovsky equation. And they also don't account for quasi-normal mode incompleteness, which I left very unspecified with those dots on the right-hand side. So this motivates trying to use different techniques, or kind of going back to the drawing board and look again at how we derived the expression for the excitation coefficients and what we left out in that process. So this was work led by Marina De Amicis, who's a postdoc at Perimeter, and also with Enrico Cannizzaro, Gregorio Carullo, and Adrian Kunz. So the setup to understand this dynamical excitation of quasi-normal modes again will be to stick to linear perturbations of a Schwarzschild background and incorporate now the source of a smaller black hole that will be inspiraling and plunging into the main black hole. And this might seem like strong assumption, a bad approximation to the gravitational wave systems we currently detect, which are more comparable masses. but there's been a lot of work in the past 20 years in the small mass ratio expansion, as it is called. And you can see that if you compare numerical relativity simulations with these small mass ratio waveforms in Schwarzschild, and if you look at the right comparison, so numerical relativity simulation with a large mass ratio, 1 to 15, and a non-spinning remnant, so that it's consistent with Schwarzschild, you actually find a very good agreement. So this will be our motivation to choose this setup, which is, of course, simpler than the comparable mass case. Okay, so we said we want to go back to the drawing board. So let's look at gravitational perturbations in Schwarzschild sourced by our point particle. So this will mean that we want to solve the Reggie-Wheeler or Zerilli equation with a source. And a beautiful tool to do this is the Green's function. So in the time domain Green's function is what we want to eventually use. But the first step will be to build the frequency domain Green's function. So if we place our observer further away than the source, so our star, our observer, and our star prime, our source, then the frequency domain Green's function can be built from this combination of independent mode solutions of the Reggie-Wheeler equation. And we choose for kind of the observer side, the outgoing solution at null infinity, and for the source side, the ingoing solution at the horizon. And W is just the Wronskian between the two solutions. We know quite well what the analytic structure of this Green's function is. It has poles at the quasi-normal mode frequencies that come from zeros of the Wronskian, and it has a branch point at omega equal to 0, which comes instead from the structure of the mode functions themselves. And so the standard law to construct now the time domain Green's function is to Laplace transform back to time. So this would have been an integral over the real line just above the branch point. But to make it more explicit that we have quasi-normal modes in our problem, we usually say we close the contour in the lower half plane and pick up the residues at the poles and some branch cut and some arc contribution. And so naively, this is what we would call the quasi-normal mode Green's function, right? The part only coming from the residues. However, this idea that we would always close the contour in the lower half plane is not quite right or quite useful, because really we want to do that only when the integral over the arc is 0 or at the very least finite, right? Rather than expressing our original integral into a sum of divergent contributions. So we want to find the condition to be able to close the contour in the lower half plane. In our work, we actually restrict ourselves to a simpler condition, which is just the requirement that the QNM sum at least converges as we sum over an infinite number of poles. And this is what the QNM sum for the Green's function looks like. There are some excitation factors that are essentially the derivative of the Wronskian or the norm of the mode. And we have what are essentially the series part of Lever's solution for the quasi-normal modes. And then this is instead the exponential part of Lever's solution. Okay, so some parts of the series are well understood analytically. For example, the behavior at large n of the excitation factors is known, and also of the frequency. But Lever series is a bit more complicated, especially if we want to, determine a convergence condition at all values of the Green's function argument. So we don't want to use any asymptotic expansions at large R star prime or R star prime going to the horizon. We want a general condition. So we resorted to exploring this numerically, and we found that the condition is the one I wrote over there. So this condition is essentially a scattering condition. It means that if our source R star prime is at positive R star, so to the right of this so-called bounce radius, R star equals 0, then the observer far away, our new cat, will receive quasi-normal mode signals once the signal has had time to scatter off the bounce radius. Instead, if the source is located to the left of the bounce radius, QNMs can propagate directly inside the light cone. And I also depicted this here. So again, to the right, we have scattering, which is more restrictive than the light cone. And to the left, instead, we have the light cone condition.
Do you guys understand why that is not a free?
Yes, so I was trying to mention here that this bounce radius is not the light ring, and it's not the peak of the potential of the Reggie-Wheeler or Zerilli potential, which is quite strange. There's been just last week or 2 weeks ago a paper by Ben Withers and his PhD student Carballo, where they found that this bounce radius is related to some complex geodesics that bounce at the singularity, and which seem to be related to the convergence radius of the quasi-normal mode sum. But yeah, that's all I can say.
That adds
Confusion, yeah, I don't know. Okay, I wanted to stress that this QNM propagation condition is not the same as causality, and therefore there will be different parts of the Green's function that are propagating with a delay with respect to each other, right? So if our source R star prime is still to the right of this potential barrier or bounce radius, we can actually split the Green's function into two pieces. One that still has the quasi-normal modes, the poles, and one that only has the branch point and branch cut. And you can split the space-time in different regions, and in these different regions, you find different convergence conditions, and therefore you need to close the contour in different ways. So what we were talking about previously was this QNM region, where you can actually close the contour for both pieces of the Green's function in the lower plane. But there is a region between the scattering condition and the light cone where you actually need to close this part of the Green's function in the upper half plane, and therefore you lose the QNMs. So this is what people have referred in the past to as the prompt response. And finally, of course, there's a region prohibited by causality where you close both Green's functions in the upper half plane and you get 0. Okay, but we want to forget, for now at least, about the branch cut and other parts of the Green's function and only focus on quasi-normal modes. And so the more appropriate definition of the quasi-normal mode Green's function needs to incorporate this propagation condition or convergence condition. And so we will have it there as a Heaviside function. Okay, so we dealt with the first piece of the puzzle. The second piece is the point particle source, which I've written down here a bit more explicitly. So this will oscillate with the orbital frequency of the particle and is localized on the particle trajectory, for which we will choose a circular in spiral that transitions to a plunge. You'll see in a moment that it's important that the point particle source has two kinds of pieces, a delta function and a derivative of the delta function. And this is important because we will convolve this source with the Green's function, right? So we will have two integrals. And the delta function can get rid of one integral, but not both. While with the derivative of the delta function, we can get rid, by integrating by parts, of both integrations. Okay, so finally we can put all these pieces together and come up with an extended definition of the excitation coefficients that takes into account this Q and M propagation and also the presence of the source. So this is what I've written over there. And I've divided it into, according to these two pieces of the source, into two types of excitations. One is this activation type excitation, which still contains an integral and therefore accumulates over the trajectory of the particle up to the apparent location of the particle as seen by the observer. And instead, the second coefficient is more of an instantaneous excitation that depends only on the apparent location of the particle and doesn't accumulate over the evolution. And of course, the apparent location needs to be determined with the right propagation condition, depending on whether you're to the right or to the left of the bounce radius. Okay, so let's finish off by looking at all this in terms of some nice plots. So the first one is kind of the main punchline. This is the full quasi-normal mode signal generated by the plunging particle. I'm adding up an increasing number of overtones of quasi-normal modes, and I'm showing kind of the largest number in pink. So that's the closest to the full quasi-normal mode signal.
Excuse me, for L equal 2?
Yeah, L equal 2. And the dashed line is instead a full numerical solution of that sourced Reggie-Wheeler or Zerilli equation, which therefore contains other parts of the signal, other parts of the Green's function, right? The branch cut, the front piece. So we see that from when the particle crosses the bounce radius, the Q and M signal actually completely reproduces the full signal, right? Which is very nice. But instead, of course, at earlier times, the front piece, the direct emission of the inspiraling particle is still very important. And therefore, the quasi-normal mode signal doesn't match at all. So to unpack this quasi-normal mode signal and actually kind of answer the original question of this talk, we can also look at these excitation coefficients as a function of time. So in the standard picture, we would have said that the amplitudes of the quasi-normal modes are constants. And instead, in this better model, we find that they evolve over time, right? They kind of peak around the crossing of the bounce radius, and then they settle onto a constant only at late times. And I think it's important to note that even after the quasi-normal mode signal has become, the dominant part of the signal, a good description of the signal, the amplitude is still not constant, not quite constant. Here I'm showing both these kind of accumulation type coefficients and these instantaneous coefficients, and they have exactly the behavior you would expect. One accumulates and the other one instead peaks around the bounce radius and then decays. And all this was for the fundamental mode. But if you look at the overtones, the picture actually is a bit different. I'll give you a second. What you can see is that these overtones, for the first overtone, you cannot see quite clearly. It seems to settle to a constant, but not quite. You cannot quite tell. But for the second overtone already, you can clearly see that it's growing at late times, its amplitude. Luckily, this is just an artifact of looking in a sense at the wrong quantity, because the actual physical observable is not the coefficient there, C or I, but rather the full waveform, which also contains, of course, the exponential decay of the quasi-normal modes. So if you look at actually the waveform of each pole, coming from each pole, you see that it does decay at late times. So everything is good. However, if you stare a bit more closely at this picture, you realize that everything is fine, but maybe not quite what you would have expected. Because you see that the fundamental mode in green is decaying at a different rate from all the other modes at late times, right? And all the other modes instead are decaying all at the same rate, which is not what you would have expected because they all have different imaginary parts to their frequency. They seem to decay at the right rate at intermediate times, but not at late times. So what's going on? Not a cat. What's going on is that what you see at late times and what Xinjiang was also finding is the role of the source. Because as you approach the horizon, the quasi-normal modes are contributing with their own personalized decays. But you're also convolving with the source, which is instead, approaching a universal horizon behavior. It's decaying at leading order with the horizon redshift. And the horizon redshift numerically is such that the source decays faster than the fundamental mode, but slower than the overtones. And therefore, at late times, you see the fundamental mode decay, but for the overtones, you see the source taking over, and therefore this redshift component. I should say that there's been some controversy in the literature. Some previous works had found that actually the leading redshift component has zero amplitude, while we don't find this. Yeah, maybe, I'm not sure why. It could be that other parts of the Green's function cancel this leading order redshift component, but I'm not quite sure. Okay. And the last thing I want to mention is that it's nice to also understand a bit more the physical mechanism of quasi-normal mode excitation. And we can understand this by looking at both the frequency of the signal, the total signal, frequency of the total signal, and also by looking at the relative phases of different modes. So what you see at early times is that the frequency is being driven by the frequency of the particle, which is this dot-dashed orange line. And the phases are approaching pi. So the modes are being excited in counter phase. And so this matches this kind of forced harmonic oscillator picture, right? The quasi-normal modes are actually kind of collectively getting excited and forced by the particle. And even though their amplitudes would be quite large, taken singularly, they are in counterphase and they are destructively interfering in this excitation. Instead, at late times, as the source has decayed, you see kind of a free oscillator, right? The frequency is approaching the frequency of the fundamental mode, and the modes are actually now in phase. There's some more dynamical transition going on at intermediate times, but at least in these two regimes, this is what we find. Okay, so this brings me towards the end. To summarize, we think by putting together actually very simple ingredients, the quasi-normal mode Green's function and the source of a point particle, that we've gained some better physical understanding of the dynamical excitation of quasi-normal modes. We've seen how the amplitudes behave over time, how they grow over time. We've seen the emergence of the source, the redshifted source at late times. And we've seen this transition from driven to free excitation. So now if you've counted all the cats correctly, I have a small treat. Stephen and I are based in Nottingham, where actually George Green was born and raised. And if you ever come to Nottingham, it's really nice to visit the Green windmill, which was owned by the Green family. So George Green worked at the family mill and was completely self-taught, which is amazing. Yeah, apparently he was working on Green's functions when there was no wind, so when he could take a break from the mill. He made all these amazing, developments in mathematics and in physics because he was self-taught and therefore was not forced to use Newton's methods for calculus like everyone else in England at the time, and could instead choose to use Leibniz's calculus. And final part of the story, he, even though he was self-taught, he really wanted to go to Cambridge or Oxford, but at the time you had to be a bachelor to attend. And therefore, even though he had several children with a woman in Nottingham, they never married, so that he could eventually go to Cambridge. And that's all.